Hello guys, my name is Felix from examsconnect.com and welcome to our physics class. We are still on measurement. It's a continuation of what we previously were learning about. Now, I want today to look at two sources of errors that occur when you're using instruments in physics calculation. Remember last time we talked of an ideal value, and we defined an ideal value as a value that cannot actually be gotten from an equipment. What causes these value differences? Why can't we get this ideal value? And the first source of error is what we call the random error. We first have the sources of errors before we define even the random error. Now, one source of error can be the human part. The human part. The scientist or the person who is carrying out the experiment might be having some issues when handling the materials that are involved. However, lack of knowledge of these gadgets can also cause a human error. The second part of error is the machine error. For the case of the machine error, this is where the calibration of the machine is not precise, hence leading to some causes of errors. Now, which are these errors that we're talking of? The first error, A, is what we call the random error. The first case is what we call the random error. And this one occurs with any experiment. It occurs with any experiment. This means that for every experiment you shall be doing in the laboratory, you are always likely to have the random error. And let us look at this example. If you look at an example of somebody trying to pick cards, picking cards from a deck or a pack of cards. Now, the error will be more pronounced as compared to an experiment that involves the adding of weights on a spring, also known as the Hooke's law. Why? Because when you're talking of random numbers, for example, when you talk of picking cards, you tend to imagine that somebody picking a card is having a random outcome as compared to somebody who is adding masses, especially if the weights or the masses are known. For example, if for the case number 2, if the masses are responding in such a manner that for every 10 newtons, we have an extension of 15 centimeters, then we don't expect errors to occur due to the Hooke's law. Because we know that from the Hooke's law, it is more of a precise results. So depending on how random the sample is, then we tend to have a more random error. So the random error occurs when the sample is also a kind of a random sample. Next, we go to the second source of error, apart from the random error, is what we call the zero error. That is B, the zero error. And we can define this by first saying that there are two types of zero errors. There are two types of zero error. We have the positive and the negative zero error. The positive and the negative zero error. And what happens is that zero errors cause systematic errors. Zero errors results to systematic errors. And when you talk of a systematic error, we are talking of an error that is kind of repetitive. A systematic error is a repetitive error, kind of an error. For example, if some people are carrying out an experiment and they notice that for this gadget A, the gadget A as compared to another gadget B that is used for the same experiment, there is always either an addition in the outcome. For example, when gadget A has something like 50 newtons, gadget B has 50.2 newtons. Then we go to another sample, then we get this one like something like 30 newtons, but this one produces 30.2 newtons. It means this kind of an error that is occurring here is more sort of a predicted error that you can predict. It becomes a systematic type of an error that is always repeating itself in a certain manner. And this error, we are saying it's caused by the zero error. So the zero error causes a systematic type of an error. Now let me give an example to expound more on the zero error. If a machine has an error of positive 2, if a machine has an error of positive 2, calculate the actual measure if the recorded measure is 18 units. Calculate the actual measure if the recorded measure is 18 units. So we're talking of this machine has an error of positive 2. And remember that this positive 2 is always causing a systematic error in the reading. Therefore, when the machine reads 18 units, it means that the 18 units are not the real units in the measured object. Therefore, can we get the real measure of the object that we are having? So in the solution that I'm going to solve here, we come and say that the actual measure is equals to the recorded measure minus the error. The recorded measure, you eliminate the error. So minus the error. Therefore, I'm going to have this as 18 units minus positive 2 units. 18 units minus positive 2 units. Therefore, we have this as 18 minus 2, giving us 16 units as the actual units of our object. 16 units as our actual units of the object. Therefore, we notice that we always need to cater for the zero error in our example, and that's why you are noting that I am subtracting the error from my example that I had given you, because the error affects our reading. And how does the zero error affect our reading? Because it creates a systematic error. And the only way you can notice the systematic error, maybe in the lab or when you are carrying out your experiment, is before even you have engaged your instrument, it's already giving you a reading. Before you engage your instrument, you notice that it is giving you a reading. For the case of a voltmeter, if I may take a case of a voltmeter, you notice that even before you give a load into the voltmeter is already giving you a negative value. That negative value is what we call the zero error, and if you're not careful with it, it will give you a systematic error in your reading. It can be a negative value, or it can also produce a positive value. And how do you differentiate between a positive zero error and a negative zero error? The positive zero error is on the positive side of your scale. For example, 2. When the voltmeter reads 2 volts, even before you've connected your load, then it means that this voltmeter has a positive zero error that you need to cater for. when you want to get the actual reading from what you're getting as recorded reading. So the hint is always subtract the error from the recorded value. Finally, I give a last example. The diameter of a tube is recorded as 21 millimeters, 22 millimeters, and 26 millimeters. The diameter of a tube is recorded as 21 millimeters, 22 millimeters, and 26 millimeters at 3 different places. So assuming that the results are anomalous, meaning that we are assuming that the person was precise and tried as much as possible to use the instruments correctly. What is the uncertainty? Calculate the uncertainty and the percentage uncertainty. Calculate the uncertainty and the percentage uncertainty in this case. So when you come to the solution part, we can solve it this way. First, you calculate the average. You calculate the average of 21, 22, and 26. The average gives us 23 millimeters. Next, we look for the half of the average. The half of the average. That gives us 2 point. So in the solution, we first look for the average of the values 21, 22, and 26. The average becomes 23 millimeters. Next, we look for the half of the range. The half of the range. Remember that the range in mathematics is defined as the difference between the highest value and the lowest value. Therefore, we are going to get the difference as 26 subtracted 21, that gives us 5. So it's a half of 5, that gives us 2.5 units. Therefore, we get the value as 23 plus or minus 2.5 units. 23 plus or minus 2.5 units. And from that, from the uncertainty, we can get the percentage uncertainty as 2. The percentage uncertainty is equals to 2.5 divided by actual times 100%. That gives us the value as 11%. 11%. Remember, it will be plus or minus 11%. The error as a percentage or the uncertainty will be plus or minus 11%. So that is all about errors and uncertainty. However, in our next session, we are going to try and see, can we define a compound uncertainty where the values are either added or subtracted to create an error, and what happens in such situations. So that is all for today's class. Thank you.